On a clear night, when the sky is dark enough and your eyes have had time to adjust, you can sometimes pick out a faint star in the constellation of Scutum. It looks like every other star, a single dim point of light, barely visible without help, easy to miss completely. You could spend your entire life under the night sky and never know it was there. But if you knew exactly where to look and you had a powerful enough telescope, you would be staring at something extraordinary. Something 19,000 light years away. Something so vast that if you took it out of its place in the galaxy and dropped it into the center of our solar system in place of our own star, its surface would extend outward past the orbit of Mercury, past Venus, past Earth, past Mars, past Jupiter, all the way out to the orbit of Saturn. It would swallow the entire inner solar system whole. The planet you are sitting on right now would be inside it. That object is called Stephenson 218. Throughout the rest of this video, we will refer to it as the Stevenson star, and it is, as far as we currently know, the largest single star humanity has ever found. Tonight, we are going on a slow walk toward this star, not just to look at it, but to understand it. To understand how stars come in sizes this extreme. To understand how we even measure something this far away. To understand why the championship of largest star has been claimed and lost and claimed again, over and over, throughout the last century of astronomy. And to understand what happens when stars this large eventually die. Because they do die. All stars do. The largest ones live the shortest lives. The Stevenson star has already burned through most of what it had to burn. Within the next few 100,000 years, possibly tomorrow, possibly never in our lifetimes, it will collapse and explode in one of the most violent events the universe is capable of producing. And when it does, we'll be able to see it from here. It's worth thinking, for just a moment, about the name of the Stevenson star. It doesn't sound like the name of something important. It sounds like a catalog entry, like a serial number, like the way you might label boxes in a storage facility. 2-18. That's because it is a catalog entry. The first part, Stevenson 2, refers to a cluster of stars discovered in 1990 by an American astronomer named Charles Bruce Stephenson. The 2 means it was the second cluster he found in a particular survey. The 18 means it was the 18th red supergiant identified within that cluster in a paper published in 2007. There's no name for this star that evokes its scale. No Greek letter, no mythological figure, no constellation honor. It's just an entry in a list. And yet, what that entry refers to, if our measurements are anywhere close to accurate, is one of the most extraordinary objects in our galaxy. A star so large that the words we have for size start to lose their meaning. This is something that happens often in modern astronomy. The most extraordinary objects often have the most clinical names. Black holes have names like Sagittarius A star, or M87 asterisk, or TON 618. Galaxies have names like NGC 1277 or ESO1 37001. Planets get names like Kepler 442b. The universe's most striking features are tagged with bureaucratic labels because they were found through systematic surveys, not by chance discovery by individual astronomers gazing in wonder at the night sky. They were identified by computer algorithms processing terabytes of data, given catalog numbers, and only later did anyone realize what they actually were. The Stevenson star is one of those, a catalog number that turned out to refer to a monster. There is something almost humbling about that. The most extraordinary objects in our universe, the largest, the brightest, the strangest were not discovered with great fanfare by individual astronomers staring at the night sky in wonder. They were found by careful, patient survey work, often by people who had no idea at the time what they were actually looking at. The romance of astronomy has, over the past several decades, shifted away from individual discovery and towards systematic mapping. Computers now do most of the work of identifying interesting objects in the data. Humans come along later, study the candidates, write the papers. The drama of recognition often happens in office buildings, looking at spreadsheets, not at telescopes. This isn't a bad thing. It's just a different way of doing science than the public often imagines. But before we get to that, we need to understand what we mean when we say the largest star, because there's something subtle in that phrase that's worth unpacking. When astronomers talk about how big a star is, they actually mean two different things, and these two things are not the same. One is mass, which is how much stuff the star is made of. The other is radius, which is how physically large the star is in space, how much volume it takes up, how far its surface extends from its center. These two measurements often go together. More mass usually means more size, but not always. And at the extremes, they actually diverge in interesting ways. The most massive star we currently know of is called R136A1. It sits in a cluster of stars in the Large Magellanic Cloud, a small galaxy that orbits our own. R136A1 is estimated to contain about 250 times the mass of our own star. That is an extraordinary amount of matter packed into a single object. By mass, R136A1 is the heavyweight champion of the known universe. But R136A1 is not very large in radius. It's only about 30 to 35 solar radii. Its gravity is so intense that it compacts all that mass into a relatively small space. The star burns at over 50,000 degrees Kelvin on its surface, and its outer layers are constantly being blown away by its own radiation. R136A1 is a hot, blue, ferocious thing, dense and bright, but not particularly large in any visual sense. Think of it this way. Imagine you have two objects on a table. One is a cannonball made of solid iron, about the size of a grapefruit. The other is a beach ball made of thin plastic, about the size of a small car. Which is more massive? The cannonball, by far. The cannonball might weigh 40 kilograms. The beach ball weighs a few hundred grams. But which is physically larger? The beach ball, by a wide margin. The cannonball is R136A1. Dense, compact, enormously massive, but small. The beach ball is the Stevenson star. Light by comparison, diffuse, swollen, but vastly larger in size. The truly large stars are different from R136A1. They are not the most massive. In fact, they're often relatively modest in mass, somewhere between 10 and 40 solar masses. Big, certainly, but nothing compared to R136A1. What makes them large is something else entirely. They are old, they are dying, and in the process of dying they have swollen outward to scales that defy what physics predicts should be possible. These dying giants are called red supergiants, and the story of finding the largest one is the story we are going to walk through tonight. The Stevenson star is the current record holder, but its measurement is also one of the most disputed numbers in modern astronomy. The size we have for it pushes against theoretical limits, limits that say stars shouldn't be able to grow this large at all. Either the limits are wrong, or our measurements of this star are. We don't fully know which one it is yet, and we may never know for certain, but we do know enough to walk through the story carefully. So that's what we'll do tonight. We're going to start with the basic physics of how stars become this big in the first place. Then we'll trace the history of largest star claims through the last 100 years of astronomy, watching champions rise and fall as measurements improve. We'll spend time understanding how we even measure something 19,000 light-years away. The challenges, the uncertainties, the assumptions baked into every number we have. Then we'll get to the current contenders. Not just the Stevenson star, but the other stars vying for the title, including one in another galaxy that we've actually seen directly. We'll explore what happens when these stars die. And finally, we'll think about what it all means, what the existence of objects on this scale tells us about the universe we live in. Lie back, settle in. We have time. The universe has been making stars like these for 13 billion years, and they're not going anywhere in the next 2 hours. The reason this matters, beyond the basic curiosity of how big can stars get, is that these monstrous stars are also the most consequential. Massive stars die violently, and their deaths shape entire galaxies. The supernova of a single large red supergiant can outshine its entire host galaxy for weeks. The expanding shockwave from such an explosion compresses surrounding gas clouds, triggering new star formation. The chemical elements released by these explosions seed the next generation of stars and planets, with everything heavier than helium, the elements that make rocky planets, oceans, and biology possible. In a real sense, stars like the Stevenson star are responsible for everything interesting in the universe. Without their deaths and the heavy elements they produce, there would be no carbon, no oxygen, no iron, no calcium. There would be no rocky planets, no liquid water, no biology, no consciousness, no us. The universe would consist entirely of hydrogen and helium drifting forever in expanding emptiness, with no possibility of complexity emerging. When we look at these cosmic giants, we're not just looking at extreme objects. We're looking at the machinery that makes the rest of existence possible. The universe is what it is, in part, because stars like these have been living and dying for billions of years, leaving their material behind for the next round. That's worth thinking about as we walk through this story. The objects we're examining tonight are not curiosities. They're, in a quiet way, our ancestors. To understand how a star gets to be the size of the Stevenson star, we have to start with how stars work in general. Every star, at its core, is a balance between two forces. The first force is gravity. A star is an enormous amount of matter, and that matter wants to fall in on itself. If there were nothing pushing back against gravity, the entire star would collapse into a single dense point in a matter of minutes. The thing pushing back is fusion. Deep inside the core of a star, the pressure and temperature are so extreme that atoms are forced together hard enough to fuse into heavier atoms. In our own star, hydrogen atoms are being fused into helium at a rate of about 600 million tons every second. Every one of those fusion events releases a tiny burst of energy, and the cumulative effect of trillions of fusion events happening every second is enough to generate radiation pressure that pushes outward against gravity, holding the star up. A star is, in a sense, a delicate balance. Gravity pulling in, radiation pressure pushing out. As long as those two forces stay matched, the star is stable. It glows steadily. It produces energy. It does what stars do. It's a balance that can last for an extraordinarily long time. Our own star has been doing this for 4.6 billion years already, and will continue to do it for roughly another 5 billion years. Throughout most of that time, the star looks almost identical from one century to the next. Slight changes in luminosity, slight variations in surface activity, but fundamentally the same object year after year, eon after eon, doing the same thing. The pace of hydrogen fusion in our own star is staggering when you stop to think about it. 600 million tons of matter are being converted from hydrogen into helium every second, with a small fraction of that mass being converted directly into energy according to the famous equation by Einstein relating mass and energy. The energy is what we see as sunlight, what warms the surface of the Earth, what allows plants to grow, what eventually becomes the chemical energy stored in food and the kinetic energy of every living thing. Every photon you have ever experienced as warmth or vision came, ultimately, from this fusion process in the core of a star. This is the main sequence phase of a star's life, the long, stable adult period. For most stars, including our own, the main sequence is when nothing dramatic happens. The star sits there, fusing hydrogen, glowing, providing the conditions that allow planets to exist around it. If life is going to develop on a planet, it almost certainly develops during its host star's main sequence phase, because this is the only period that lasts long enough for biological evolution to play out. But the main sequence doesn't last forever. Eventually, every star runs out of fuel. And what happens then depends on how much fuel the star started with, which is determined by its mass. The size and behavior of a star depend on how much mass it has, because mass determines how much gravity is pulling inward, which determines how hot and dense the core has to be to push back. Small stars with less mass have gentle cores and burn slowly. They're cool, they're dim, and they live for a very long time. A red dwarf, the most common kind of star in the galaxy, has about 1/10 the mass of our Sun and will live for trillions of years before it runs out of fuel. Our own star is medium-sized, roughly 4.6 billion years into a roughly 10 billion year main sequence lifespan. It burns hydrogen in its core at a relatively modest pace. It will continue to do this for another 5 billion years or so before things start to change. The largest stars, the ones we're interested in tonight, started life much more massive. They were born with 10 to 40 times the mass of our star. And massive stars don't burn fuel gently. They burn it furiously. The cores have to be vastly more hot and dense to hold up against all that mass pulling inward. Fusion rates are orders of magnitude faster. A star with 25 times our Sun's mass will burn through all its core hydrogen in just 7 to 8 million years. And it's what happens at the end of that main sequence lifetime that's important for the story we're telling. When a massive star exhausts the hydrogen in its core, the balance breaks. There's no more fuel to fuse, so the radiation pressure drops. Gravity starts to win. The core contracts. As the core contracts, it heats up. Temperatures rise high enough that helium, the byproduct of all that hydrogen fusion, begins to fuse into carbon. And here's the strange part. While the core is contracting and getting hotter, the outer layers of the star do the opposite. They expand. The energy from the new helium fusion in the core, plus the energy from a shell of hydrogen still burning around the core, pushes the outer layers of the star outward. The star bloats. It cools because its surface area is increasing faster than its luminosity. The color shifts from white or yellow to orange to red. The star has become a red giant. For a star like our Sun, this red giant phase will be impressive, but not catastrophic. Our Sun, when it eventually reaches this stage in about 5 billion years, will expand to perhaps 200 times its current radius. It will reach the orbit of Earth, possibly. The exact end state is still debated, but it's going to be bigger than anything you've ever imagined a star could be. Now imagine that, but with a much more massive star. a star that started life with 20 times our Sun's mass. When that star exhausts its core hydrogen and starts the red giant transition, it doesn't just expand to 200 times its original size. It expands further, much further. It becomes a red supergiant. A red supergiant is not just a bigger red giant. It's a different category of object entirely. Red supergiants can reach radii of 500, 800, 1,000, 1,500 solar radii. Their outer atmospheres become so extended, so tenuous, that gravity can barely hold them in place. The star starts shedding material into space at enormous rates. Every 100,000 years or so, a red supergiant loses about an Earth mass worth of matter from its outer envelope. The lost matter forms a glowing nebula around the star, often visible as a dusty cocoon in infrared images. The interior of a red supergiant is a complicated place. While the outer envelope is expanding and cooling, the inner core is doing something almost the opposite. Each time the core finishes fusing one element, it contracts and heats up enough to start fusing the next heavier element. Hydrogen first, then helium, then carbon, then oxygen, neon, silicon, in increasingly rapid succession. What's strange is the timeline. A massive star spends the first 90% of its life on the main sequence, fusing hydrogen. That phase lasts maybe 8 million years. Then it transitions to helium fusion, which lasts about 700,000 years. Then carbon fusion, which lasts a few hundred years. Then neon fusion, lasting a few months. Oxygen fusion, lasting a few weeks. Silicon fusion, lasting a single day. Each stage is shorter than the last because each stage produces less energy per atom of fuel, while the gravity trying to crush the core remains constant. The star, in its final years, is rushing through a series of increasingly desperate attempts to keep burning. The outer envelope continues to expand throughout, oblivious to the chaos in the deep interior. From outside, the red supergiant looks almost the same throughout, a slow, bloated, cool red object, gradually pulsing, gradually shedding mass, gradually dying. These stars don't last long in this state. The entire red supergiant phase, from start to finish, lasts maybe 100,000 to a few 100,000 years out of the star's total multi-million-year lifespan. We're catching them at the very end of their lives. There's a theoretical limit to how large red supergiants can get. It's called the Hayashi limit, after the Japanese astrophysicist Chushiro Hayashi, who first calculated it in the 1960s. The Hayashi limit predicts that a red supergiant of a given mass cannot expand beyond a certain radius before becoming dynamically unstable. The outer envelope becomes so loosely bound that it falls apart faster than the star can replenish it. For typical red supergiant masses, this theoretical ceiling works out to about 1,500 solar radii. That's the theoretical ceiling. Past that point, stars shouldn't be able to exist in stable form. This is going to matter, because some of the stars we're going to talk about appear to exceed this limit. The Stevenson star, at a claimed 2,150 solar radii, is well past it. There are two possibilities. The first is that this theoretical ceiling is more flexible than we think, and stars can grow larger than current theory predicts under unusual conditions. The second is that our measurements of stars, like the Stevenson star, are wrong, and they're not actually as large as we've been claiming. Both possibilities are plausible. Both are taken seriously by working astronomers. We'll come back to this question. But for now, what matters is this: red supergiants exist. They are the biggest objects of their kind in the universe, in terms of physical size. They live short lives at scales that strain the laws of physics, and they die spectacularly. When a red supergiant runs out of options, when it has fused everything it can fuse, and there's no more fuel left to push back against gravity, the core collapses. In a matter of seconds, gravity wins completely. The core falls in on itself, becoming either a neutron star or, if the star was massive enough, a black hole. And the rest of the star, all those expanded outer layers, gets blown outward in a supernova explosion. For a brief period, a few weeks, maybe a single dying star produces more energy than entire galaxies. The light is visible across the universe. Sometimes, from our position on Earth, we can see it. In the year 1054, Chinese astronomers recorded a guest star that appeared in the sky and was visible during daylight for 23 days. They didn't know what it was. We do now. It was a red supergiant in our own galaxy, dying. The remnant of that explosion is what we now call the Crab Nebula, and inside the nebula is a rapidly spinning neutron star, all that's left of a star that was probably about 10 times our sun's mass when it began. Stars like the Stevenson star will end the same way. We're watching the closing chapter of a life that started somewhere between 20 and 40 million years ago, when a cloud of gas in the Scutum Centaurus arm of our galaxy collapsed and ignited. Most of that life has already been lived. What we're looking at now is the swollen, dying remnant of something that used to be a much smaller, much hotter, much more compact star. The largest stars in the universe are not in their prime. They are in their final form, and their final form is enormous. The history of the largest known star is more than anything else a history of measurement getting better. For most of human history, the largest stars we knew of were just the brightest reddish ones we could see with our eyes. The ancients knew them by name: Antares, the heart of Scorpio; Betelgeuse, the shoulder of Orion; Aldebaran, the eye of Taurus. These stars were noticeably red, suggesting cool surface temperatures, and they were among the brightest objects in the night sky, suggesting either enormous luminosity or close proximity, or both. The name Antares is actually a clue. It comes from the ancient Greek meaning rival of Ares. Ares being the Greek god of war, associated with the planet Mars. The Greeks named Antares this way because the star is the same color as Mars, and during certain times of year the two appear close together in the sky. The Greeks didn't know that Antares was a red supergiant 550 light-years away. They just noticed it was red, like Mars. Their naming captured something true about the star's nature, in a way that wouldn't be understood scientifically for another 2,000 years. Betelgeuse is similar. Its name comes from Arabic, meaning roughly the hand of the giant, referring to its position in the constellation we now call Orion. The Babylonians, the Egyptians, the Chinese, every civilization with sustained astronomical traditions noticed Betelgeuse. It's one of the 10 brightest stars in the night sky, easily visible, distinctly orange-red, and prominent in a constellation that contains some of the most recognizable star patterns from any culture. But none of those ancient astronomers had any way to know how big these stars actually were. They could measure brightness, they could measure color, they could measure positions in the sky. They couldn't measure size because they didn't know how far away the stars were. And without distance, you can't tell whether something is big and far or small and close. It wasn't until the 19th century, when stellar parallax was first successfully measured, that astronomers could start putting distances on stars. The first successful parallax measurement was made in 1838 by Friedrich Bessel. measuring the distance to a star called 61 Cygni. That single measurement was a turning point in astronomy. For the first time, the universe had a real scale. Stars were not equidistant points pasted on a celestial sphere. They were at different distances. Some were close, some were far, and astronomers could finally start to determine which was which. Even then, only the closest stars yielded to parallax measurement. Stars like Betelgeuse and Antares, both several hundred light years away, were on the edge of what 19th century techniques could handle. The measurements existed, but they came with wide error margins. Astronomers knew Betelgeuse was somewhere between 400 and 700 light years from Earth. The exact distance wouldn't be pinned down for another century. As measurements improved through the 20th century, the picture started to fill in. By the mid-1900s, astronomers had a rough idea of which nearby stars were the largest. Betelgeuse came in at around 600 to 900 solar radii, Antares around 700. Mu Cephei, also known as Herschel's Garnet Star, came in around 1,000 to 1,200 solar radii. These were genuinely enormous objects. If you placed Betelgeuse at the center of our solar system, its surface would extend out somewhere between the orbits of Mars and Jupiter. For most of the 20th century, these familiar naked-eye stars were considered the largest known, but they were nearby. They were close enough that we could see them clearly. There was no particular reason to think the largest star in the galaxy happened to be one of the ones we could see without help. Statistical reasoning suggested that there were probably much larger stars further away, beyond our ability to measure them at the time. The galaxy is full of stars we cannot see. The Milky Way contains hundreds of billions of stars, and we can only see a few thousand of them with the naked eye. The brightest stars in our sky are mostly nearby. The largest stars in the galaxy are mostly far away, hidden by distance and by dust. There's no reason to expect the brightest visible star and the largest existing star to be the same object. They usually aren't. In the late 20th century, that started to change. New telescopes, new techniques, and new infrared surveys started revealing red supergiants in regions of the galaxy that had previously been obscured by dust. Many of the most extreme red giants in the galaxy turned out to be in the Scutum and Cepheus constellations, hidden inside dense star-forming regions that absorb visible light. The first big shake-up came with VY Canis Majoris. This is a star in the constellation Canis Major, about 4,000 light-years from Earth. It's a red hypergiant even more extreme than a red supergiant. In the 1970s and 1980s, as VY Canis Majoris was studied more carefully, the size estimates came in extraordinarily large. Some researchers calculated radii as high as 2,800 to 9,300 solar radii. If those numbers had been correct, VY Canis Majoris would have been one of the largest single objects ever observed. But the numbers were extraordinarily uncertain. The star is heavily obscured by dust. Its outer atmosphere is so extended and so variable that it's hard to define where the star actually ends. Different measurement techniques gave wildly different answers. Over decades, as measurements improved, VY Canis Majoris's estimated radius came down and down and down. Current best estimates put it at around 1,420 solar radii. Still enormous. Still among the most extreme stars we know about. But not 9,000, not even 3,000. The early measurements were off by factors of 2 or 3 due to bad distance estimates and confusion about where the star's surface actually was. This pattern would repeat. A star would be measured. The number would be extraordinary. The star would be hailed as the new largest. Years later, with better data, the number would come down. By the late 1990s and early 2000s, VY Canis Majoris had been displaced by other contenders. The constellation Cepheus, in particular, turned out to host several enormous red supergiants: Mu Cephei, KW Sagittari, VV Cephei A. Different studies name different stars as the largest at different times. There was no consensus. Then came UY Scuti. UY Scuti is a red hypergiant in the constellation Scutum, the same constellation that hosts the Stevenson star. In 2012, a team of astronomers using a combination of infrared imaging and stellar atmosphere modeling published a new size estimate for UY Scuti. The result was 1,708 solar radii. At the time, this was the largest well-measured radius of any single star. UY Scuti held the throne for years. It became famous. It appeared in popular science articles, YouTube videos, scale comparison diagrams. For a generation of space enthusiasts, UY Scuti was simply the largest star. Many people still think of it that way. Then, in 2018, the Gaia Space Telescope released its second data release. Gaia is a European Space Agency mission that measures the precise positions and distances of billions of stars in our galaxy. For nearby stars, Gaia's measurements are extraordinarily accurate. For more distant stars, Gaia still helps refine our distance estimates significantly. When Gaia's distance measurement for UY Scuti came in, the implications were dramatic. The new distance was significantly smaller than the value used in the 2012 study. Smaller distance means lower intrinsic luminosity for the same apparent brightness. Lower luminosity means smaller physical size to produce that luminosity at that temperature. UY Scuti's radius estimate collapsed. New calculations using Gaia distances put the star at somewhere between 755 and 909 solar radii, less than half its previous estimate. UY Scuti is still a massive red supergiant. It's still vastly larger than our own star. But it's not the largest star anymore. It's not even close. This kind of revision is sobering. UY Scuti was famous for being the biggest. Now it's not. The star itself didn't change. We just learned that we had been measuring it wrong. The Gaia mission's role here is worth dwelling on for a moment. Gaia is the most ambitious astronomical survey ever undertaken. The spacecraft sits at a stable gravitational point about 1.5 million kilometers from Earth, spinning slowly, scanning the sky continuously. It measures the position of every visible star, hundreds of times over its operational lifetime. By comparing positions at different times across the year, it can detect parallax shifts of stunning precision better than 10 micro-arcseconds for the brightest stars. To put that in perspective, 10 micro-arcseconds is the angular size of a coin held at the distance of the Moon. Gaia can detect parallax shifts that tiny. The accuracy is so high that for many nearby stars, Gaia has redefined what we know about their distances, their luminosities, and their physical sizes. The result has been a sweeping recalibration of stellar astronomy. Stars whose properties had been considered well established for decades have had to be reconsidered. Stars, whose distances were thought to be known to within 10%, have been refined to within 1%, and the new numbers are often significantly different from the old ones. UY Scuti was one of the casualties. So were a number of other extreme stars. The Gaia era has been a chastening period for largest and most luminous claims. Many of them have been revised downward as the distances got more accurate. Every star on the historical list of largest known has eventually been revised. Most have been revised downward. The pattern is consistent. we study a star with the best techniques available. We declare it the largest. Years or decades later, better techniques come along, and the measurement gets refined. Usually, the new number is smaller than the old one. Sometimes it's much smaller. The lesson is consistent. Confidence in a measurement is not the same as accuracy. We can be very confident in a particular number and still turn out to be wrong by a substantial fraction. This is not anyone's fault. It's how the science works. The best we can do is measure as carefully as possible with current tools, publish honestly, and revise when better tools come along. And this is where the Stevenson star enters the story. In 1990, an American astronomer named Charles Bruce Stephenson conducted a deep infrared survey of the galaxy. Infrared light penetrates dust much better than visible light, allowing astronomers to see through dense interstellar regions that block normal observation. Stephenson was looking for red supergiants in the galactic plane, and he found them in clusters. One particular cluster, which Stevenson identified in 1990, was located in the Scutum constellation. It became known as the Stevenson 2 cluster, or RSGC2. It contained dozens of red supergiants packed together in a relatively small region of space. The cluster is enormously massive, somewhere between 30,000 and 50,000 times the mass of our Sun, in stellar matter and only about 14 to 20 million years old, making it a young cluster by galactic standards. For 17 years after its discovery, the Stevenson 2 cluster was studied, but not in particular detail. It was one of several massive red supergiant clusters near the inner Milky Way, all of which contained interesting stars worth measuring. The reason these clusters had remained obscure for so long is straightforward. They sit in directions of the sky where dust between Earth and them blocks most visible light. To the naked eye, looking toward the constellation Scutum reveals only the faintest impression of the Milky Way passing through, with no hint of the dense star-forming activity going on behind the veil of dust. The cluster had to be discovered through infrared observation, which can penetrate dust much better than visible light. For most of astronomical history, the technology to do this kind of survey didn't exist. The first infrared surveys capable of finding clusters like this only began in the late 20th century, when detector technology and computer processing finally caught up to what was needed. In 2007, a team led by Ben Davis published the first detailed analysis of the Stevenson 2 cluster's members. They identified individual stars within the cluster, measured their properties as best they could, and gave them designations. The brightest star in the cluster was given the simple designation of 1 Stevenson 2 DFK1 or RSGC201, or by another naming convention, the Stevenson star. In 2012, another team using the Australia Telescope Compact Array, or ATCA, combined with a sophisticated dust modeling technique called DUSTY, published a new analysis of the Stevenson star. The team applied the Stefan-Boltzmann relationship. Knowing the star's apparent brightness, its surface temperature derived from its infrared spectrum, and its distance based on cluster membership, they could calculate its actual physical radius. The result was 2150 solar radii, vastly larger than UY Scuti's then current estimate, larger than any other star ever measured. When that number was published, the Stevenson star took the throne. It has held it ever since. But the throne is not entirely secure, because the 2150 number depends on a chain of assumptions, any one of which, if wrong, brings the number down. And astronomers have been arguing about those assumptions for over a decade. A star 19,000 light-years away looks like a single dot of light, even in our most powerful telescopes. There is no way to take a ruler to it. There is no way to see its disk, to outline its edges, to measure its diameter directly the way you might measure the width of a coin. So how do we know how big it is? The answer involves combining three different measurements: how bright the star appears in our sky, how hot its surface is, and how far away it is. If we know those three things, we can calculate the star's actual physical size. The principle is straightforward. A hotter object emits more energy per unit area of its surface. The relationship is governed by something called the Stefan-Boltzmann law, which was worked out in the late 19th century. The total energy a star radiates per second, its luminosity, is proportional to the fourth power of its surface temperature multiplied by its surface area. If we know the star's luminosity and we know its surface temperature, we can solve for its surface area. And surface area gives us radius. The math is unambiguous. The only difficulty is getting the inputs right. Surface temperature, as it turns out, is the easiest of the three measurements. The temperature of a star's surface determines the colors of light it emits. A cool star emits mostly red and infrared light. A hot star emits white, blue, and ultraviolet light. By analyzing the spectrum of a star, the precise distribution of colors in its emitted light, astronomers can determine its surface temperature very accurately. For the Stevenson star, the temperature is about 3200 Kelvin. That's about half as hot as our sun's surface, which is around 5800 Kelvin. The second measurement, apparent brightness, is also relatively straightforward. We measure how much light from the star is reaching our telescopes. This part is easy in principle, although it gets complicated by dust between us and the star, which absorbs some of the light before it reaches us. For the Stevenson star, we can measure how bright it appears in infrared light, then make corrections for dust absorption to estimate how bright it would appear if there were no dust in the way. The third measurement is the hard one: distance. For nearby stars, we can measure distance using parallax. As the Earth orbits the Sun, our viewpoint shifts. Nearby stars appear to shift their positions slightly against the background of more distant stars. The angle of that shift, combined with the size of Earth's orbit, gives us the distance to the star using straightforward geometry. This is the same technique surveyors use to measure distances on Earth. The principle is intuitive if you hold your finger up in front of your face and alternate closing each eye. Your finger appears to shift position relative to the background. That shift is called parallax, and the closer your finger is to your face, the bigger the shift. Move your finger far away, and the shift becomes too small to see. The same principle applies to stars, except that the two viewpoints are Earth's positions in its orbit 6 months apart, and the finger is a star far away. For the nearest stars, the parallax shift over 6 months is roughly 1 arcsecond, about the same angle as a single human hair viewed from across a football field. That's small, but it's measurable. For more distant stars, the shift is much smaller. By 1,000 light-years out, parallax shifts are measured in milliarcseconds. By tens of thousands of light-years, the shifts approach the limits of even our best instruments. Parallax works beautifully for stars within a few thousand light-years. The Gaia Space Telescope, mentioned earlier, has measured parallax distances to over 1 billion stars. For most of those stars, the measurements are excellent. But the Stevenson star is approximately 19,000 light-years away. At that distance, the parallax shift is so tiny that even Gaia's exquisite precision struggles. The measurement exists, but the error bars around it are wide. We can't pin down this star's distance to within a few percent the way we can for nearby stars. So, astronomers fall back on a different approach. They estimate the Stevenson star's distance based on its cluster membership. The argument goes like this. If this star is genuinely a member of the Stephenson 2 cluster, then it must be at roughly the same distance as the cluster as a whole. And the cluster's distance can be estimated from the average properties of all its members combined, which gives a more robust answer than trying to measure any single member. The cluster's distance, estimated this way, comes out to about 19,000 light-years, give or take maybe 2,000 light-years in either direction. But here's the subtle problem. The argument that the Stevenson star is at the cluster's distance depends on the assumption that this star is actually a cluster member. If it isn't, if it's just a foreground or background star that happens to appear in the same direction as the cluster but is actually at a different distance, then the whole size estimate is based on wrong inputs. Some astronomers have raised exactly this concern. They've noted that the Stevenson star has slightly unusual properties compared to the other members of the cluster. Its brightness, its position on the cluster's outer edge, its slightly atypical motion through space, and have suggested it might not actually be part of the cluster after all. If the Stevenson star is closer to us than the cluster, its true luminosity is lower than we've been calculating, and its radius is therefore smaller. If it's farther away, its radius is larger. The 2150 solar radii number assumes the cluster distance is right, give or take a substantial margin of error. There are other complications too. Red supergiants don't have hard, well-defined surfaces. Our own star has a relatively crisp surface. There's a clear boundary between the photosphere, where light escapes freely, and the chromosphere above it, where the gas becomes too thin to emit much light. You can take a photograph of the sun and see its edge. Red supergiants are different. Their outer atmospheres are extended, diffuse, and complicated. They have multiple layers, a photosphere, a chromosphere, a region of cooler material above that, and often an extended molecular envelope where carbon monoxide and water vapor exist. Beyond that is often a thick shell of dust ejected by the star over time. Where does the star end and space begin? It depends on how you define it. Different definitions give different radii. Imagine trying to measure the size of a cloud. A cloud doesn't have a clear boundary either. Where the cloud is depends on what you mean by the question. The dense visible center is obvious. The outer wisps are less defined. The water vapor that has dispersed from the cloud is no longer cloud technically, but where did it stop being cloud? The transition is gradual. There's no single right answer. Red supergiants present a similar problem, but on a vastly larger scale. The dense inner core is clear. The outer atmosphere fades gradually into space. The molecular envelope might be considered part of the star or not, depending on your definition. The dust shell is definitely not part of the star, but it's so close that it gets included in some measurements by accident. Astronomers have to choose a specific definition for where the star ends and stick with it consistently. For the Stevenson star, the radius estimate uses what's called the Rosseland mean photosphere, basically, the depth at which light starts being able to escape freely. This is a reasonable definition, but it's not the only one. If you defined the radius based on where the molecular envelope ends, the number would be much larger. If you defined it based on where the gas first becomes opaque, the number would be smaller. There's some judgment involved. There's also variability. Red supergiants pulse. Their outer envelopes expand and contract over months and years. The Stevenson star's brightness varies. As it pulses, its physical radius almost certainly changes too. The 2150 solar radii number is an average. The actual size in any given moment might be larger or smaller. The pulsation can be substantial, Betelgeuse, the most studied red supergiant, varies in brightness by approximately 1 full magnitude over irregular cycles of months to years. That corresponds to changes in physical size of perhaps 15 to 20%. The same is almost certainly true of the Stevenson star, though the more distant target makes the variations harder to measure precisely. So when we say the Stevenson star is 2150 solar radii, what we really mean is, on average, taken across pulsation cycles, with all our assumptions about distance and surface definition, our best estimate puts the radius at approximately 2150 solar radii. The number is real. It's just much less precise than it sounds when you say it as a single figure. And there's the constant outflow of material. The Stevenson star is shedding material constantly. The cocoon of ejected material around it is dense and uneven. Some of what we see as the star might actually be material that has already been ejected. Some of what we might think of as the star's atmosphere is actually a slowly expanding cocoon of stuff that left the star centuries or millennia ago. The mass loss is happening through what's called a stellar wind, a continuous outflow of gas and dust from the outer envelope. For an average star like our own, the stellar wind is gentle, losing only a tiny fraction of the star's mass over its entire lifetime. For red supergiants, the wind is enormously more powerful. The star might be shedding 1 Earth mass of material every 100,000 years, but at its scale, that adds up. Over a few million years, the star can shed substantial fractions of its original mass. This envelope of ejected dust can be many times larger than the star itself. The dust scatters and absorbs infrared light. When we look at the Stevenson star with our telescopes, we don't just see the star, we see the star plus its surrounding dust envelope, all blurred together by the limits of our angular resolution. Disentangling the two is one of the hardest parts of the measurement problem. All of these factors, uncertain distance, ambiguous surface definition, intrinsic variability, dust contamination, possible non-membership in the cluster, combine to give the 2150 solar radii number a substantial uncertainty. Different analyses have come out with values ranging from about 1900 to about 2400 solar radii, depending on which assumptions are used. That's a range of about 500 solar radii, which, just to put in perspective, is itself larger than most red supergiants we know. The margin of error in the Stevenson star's size estimate is bigger than the entire size of many other extreme stars. This is what makes the question of what is the largest known star so difficult to answer cleanly. We have a measurement. It's a real measurement. It was done by competent astronomers using sound techniques, but the error margins on that measurement are large enough that we can't say with confidence whether the Stevenson star is really the largest or whether the championship actually belongs to a star whose measurement is more confident but whose nominal radius is smaller. In a sense, every claim of largest star is tentative. They depend on the best measurements we have at the moment, and those measurements keep getting better, which keeps changing the answer. This is not a failure of science. It's how science works. We observe as carefully as we can with the tools at hand, we publish our results, and we revise them as new data comes in. The story of stellar size measurement is a slow accumulation of better and better data, with the largest star title shifting as the data improves. The Stevenson star currently sits at the top of the list. It might hold it for a long time, or new data, sometime in the next 10 years, might shift the ranking again. Let's spend some time with the Stevenson star itself. The full name of the star in formal astronomical catalogues is RSG C218, or alternatively Stevenson 2 DFK1, depending on which naming convention you prefer. RSGC stands for Red Supergiant Cluster 2, and the Stevenson star was the 18th red supergiant identified in that cluster. The DFK naming comes from the 2007 paper that first catalogued individual members of the cluster. Davies, Feiger, and Kudryavtsky were the lead authors. The star itself is classified as spectral type M6. The M designation means it's a cool red star at the very bottom of the temperature scale for stars. The 6 is a subclass that places it among the coolest red stars. Its surface temperature is approximately 3200 Kelvin. For comparison, the surface of our Sun is about 5800 Kelvin. The surface of an incandescent light bulb filament is around 2700 Kelvin. The Stevenson star is barely hotter than a household light bulb in terms of surface temperature. The reason it produces so much light, despite being cool, is its enormous surface area. The star is so large that even at relatively low temperatures, the sheer extent of its glowing surface produces a luminosity hundreds of thousands of times greater than our own star. Estimates of the Stevenson star's luminosity vary widely, anywhere from 90,000 to 630,000 times the luminosity of our Sun, depending on which study and which assumptions are used. The figure most commonly cited, the one used in the radius calculation, is about 440,000 solar luminosities. That means this star radiates 440,000 times more energy per second than our Sun does. If the Stevenson star were placed at the distance of our nearest stellar neighbor, Proxima Centauri, which is about 4.2 light-years from Earth, it would be one of the brightest objects in our night sky. It would be visible during daylight. It would cast shadows on clear nights. It would dominate the sky in a way that no current star except our own does. The actual radius of the Stevenson star, taking the standard estimate of 2150 solar radii, works out to approximately 1.5 billion kilometers. To put that in human terms, light, traveling at 300,000 kilometers per second, takes about 9 hours to circle the surface of this star once. Light circles our own star in just 14.5 seconds. Think about that for a moment. Light is the fastest thing in the universe. Nothing physical can move faster. And yet, to travel around the equator of the Stevenson star just one time, even at the absolute speed limit of physics, would take light most of a working day, 9 hours. The same amount of time many of us spend at our jobs. The same amount of time it takes to fly from Europe to the east coast of North America. A photon going at maximum possible speed takes a full workday to go around this star once. The volume of the Stevenson star is approximately 10 billion times the volume of our own star. You could fit 10 billion stars the size of our own inside this star with room to spare. Let me put that another way. If you shrunk our entire star down to the size of a grain of sand, say 0.5 millimeter, across the Stevenson star at the same scale would be about 1 meter across. The size of a small refrigerator. That's the actual ratio between these two objects. Both of these are stars. They're built out of the same kind of matter, doing the same kind of fusion. One is just at the end of its life and has bloated to a scale that defies imagination. Or another comparison. The Earth has a circumference at the equator of about 40,000 kilometers. If you could somehow fly an airplane around the equator of the Stevenson star at the speed of a commercial jet about 900 kilometers per hour, it would take you over 1 million years to complete the journey. You would be born, live a full life, die. Your civilization would rise and fall many times over, and your descendants would still be flying that plane around the star. Not because the plane was slow, but because the star is unimaginably large. If you took the Stevenson star out of its place in space and dropped it into the center of our solar system, in place of our Sun, here is what would happen. The orbit of Mercury is approximately 58 million kilometers out from our star. The Stevenson star's surface extends out to 1.5 billion kilometers. So Mercury, at its full orbital distance, would be deep inside the star. Mercury would be vaporized. But vaporized understates what would actually happen. Mercury isn't just a planet. It's a small rocky world with mountains and craters, and even though it's the closest planet to our Sun, it can hold solid rock together because the actual temperature of its surface is only about 700 Kelvin in direct sunlight. Inside the Stevenson star, conditions are completely different. The interior temperature climbs rapidly with depth. Even relatively far inside the outer envelope, temperatures reach thousands of degrees. Mercury would not just melt, it would ionize. Its atoms would be stripped of their electrons and would become a plasma, indistinguishable from the rest of the star's material. The orbit of Venus is approximately 108 million kilometers from the center. Venus would also be inside the star, vaporized. Same fate. Earth orbits at 150 million kilometers. That's one astronomical unit, the basic distance unit for measuring our solar system. Earth would be inside the Stevenson star. The entire surface of Earth, every continent, every ocean, every living thing, every human structure, all gone in seconds. Imagine, just for a moment, what that would look like from inside. The blue sky we have today exists because Earth's atmosphere scatters sunlight, with the shorter blue wavelengths scattering more than the longer red ones. Inside the Stevenson star, there would be no sky. The atmosphere itself would be stripped away by the surrounding stellar plasma in seconds. The surface temperature would climb past the boiling point of water, past the melting point of rock, past the temperature at which atoms can hold themselves together. Everything would dissolve into plasma, hot ionized gas, indistinguishable from the rest of the star. It would all happen in seconds. Less time than it takes to read this paragraph. Mars orbits at 228 million kilometers, also inside the star. Mars has a thin atmosphere and frozen polar ice caps. None of that would survive. The polar ice caps would sublimate, then ionize. The rocky surface would melt, then vaporize, then ionize. Phobos and Deimos, the two small moons of Mars, would be lost almost instantly. Jupiter orbits at 778 million kilometers, still inside the Stevenson star by a wide margin. Jupiter is the largest planet in our solar system itself, an enormous object with a mass over 300 times that of Earth. But even Jupiter would be lost. The hydrogen and helium that make up the gas giant would simply become part of the star's outer envelope. The Galilean moons, Io, Europa, Ganymede, Callisto, would be vaporized along with the rest. Europa's subsurface ocean, possibly home to its own forms of life, would be destroyed before any of those potential life forms could even register that something had changed. Saturn orbits at approximately 1.43 billion kilometers just inside the surface of the star. Saturn would also be vaporized, though it would be near the outer edge. The famous ring system would dissipate. The moons, Titan, with its hydrocarbon lakes and thick nitrogen atmosphere, Enceladus, with its subsurface ocean, all the others would be lost. Uranus, at 2.87 billion kilometers, would finally be outside the star. So, if you replaced our Sun with the Stevenson star, our entire inner solar system out to and including Saturn would be inside the star. Only the outer planets Uranus, Neptune, and the Kuiper Belt would survive. But survive. is also an understatement of what those outer planets would experience. Even though they would be outside the star itself, they would be in a fundamentally changed environment. The Stevenson star is hundreds of thousands of times more luminous than our own star. Uranus, currently a cold and distant planet, would suddenly be receiving as much heat from its star as we currently receive from ours. Its atmosphere would heat up dramatically. Its frozen surface would melt and possibly vaporize. The same would happen to Neptune. Even Pluto, far out in the Kuiper belt, would feel the difference. Its surface temperatures, currently around 40 Kelvin, would rise into the hundreds. There would be nothing left of our solar system as we know it. The inner planets gone, swallowed. The outer planets transformed beyond recognition. The asteroid belt, the Kuiper belt, the comets, the dust, all rearranged, all heated, all changed. This is the scale we're talking about. If you've made it this far in the video and you're finding this fascinating or just relaxing, consider hitting the like button or subscribing to the channel. It helps the algorithm understand that people want long-form, calm content like this. It costs you nothing. It helps me keep making videos. Now, back to the star. The surface of the Stevenson star itself, if we could see it up close, would not look like the smooth surface of our own star. It would look chaotic. Red supergiants don't have stable, gentle surfaces. They convect. Enormous cells of hot gas rise from deeper inside the star, reach the surface, cool, and sink back down. The convection cells in this star are estimated to be larger than our entire solar system. A single convection cell individually is larger than the orbit of Pluto. You could fly a spaceship across one convection cell on the Stevenson star, and at any speed humans have ever achieved, the journey would take many thousands of years. To grasp what this means, consider the surface of our own star. The Sun has convection cells too. They're called granules, and you can see them in high-resolution images of the solar surface. Each granule looks like a small bright cell with darker boundaries, like the cracks between tiles on a kitchen floor. A typical solar granule is about 1,000 kilometers across, roughly the distance from Berlin to Madrid. Now scale that up. One of these cells on the Stevenson star is not 1,000 kilometers across, it's billions of kilometers across. A single convection cell is larger than the orbit of Neptune. Each is its own enormous churning mass of hot stellar plasma, rising from depths we can barely conceive of, reaching the surface, cooling slightly, and sinking back down to be reheated. The whole star is essentially boiling, but the boil cycle takes years instead of seconds. The atmosphere of the star pulses. Spectroscopic observations show that different regions of the surface have different temperatures, variations of several hundred Kelvin across the visible disk. This is convection cells of hot material breaking through the surface and gradually dissipating. The star is, in a real sense, alive in a way that smaller stars are not. It is constantly churning, constantly losing mass, constantly throwing material out into space. This is not a dead, inert object. This is a hyperactive, dying star, behaving in ways that no smaller star can. The extremity of its conditions makes it dramatic in ways that calmer stars are not. The outflow of material is substantial. The Stevenson star sheds an Earth mass into space roughly every 100,000 years. Over the course of its remaining lifetime, maybe 1,000,000 years or so, possibly much less, it will lose a substantial fraction of its total mass through these stellar winds. The escaped material forms a slowly expanding shell of dust around the star, glowing faintly in infrared light, gradually mixing with the interstellar medium. That dust contains heavy elements that were forged inside the star during its fusion processes: carbon, oxygen, nitrogen. Some of those elements will eventually be incorporated into future stars, future planets, possibly future forms of life. Stars like the Stevenson star are, in addition to being extraordinary objects in their own right, the chemical factories of the universe. The elements you're made of were forged in stars like this one, in earlier generations, long before Earth existed. There is something poetic about that. The star we are looking at, in its slow dying, is contributing to the next generation of stars and planets. The matter that is now being shed by the Stephenson star will, billions of years from now, be part of something else. Maybe new stars, maybe new worlds, maybe new forms of consciousness, on some distant planet, looking up at their own night sky and wondering as we do where everything came from. The answer, in part, is from objects like this, burning out, throwing their materials into the dark, making room for what comes next. But the Stevenson star is not the only star in this conversation. There's another contender, in another galaxy, that might be more important even though it's slightly smaller. That star is called WOHG 64. WOHG 64 is located in the Large Magellanic Cloud, a small galaxy that orbits our own Milky Way. The Large Magellanic Cloud is about 160,000 light-years away. That's roughly 8 times more distant than the Stephenson star, far beyond anything we can normally study in detail. The Large Magellanic Cloud itself is one of the closest galaxies to our own. It's visible from the southern hemisphere with the naked eye, looking like a faint fuzzy patch in the sky. Magellan, the explorer, recorded it during his circumnavigation of the globe in the early 1500s, though indigenous peoples in the southern hemisphere had been aware of it for far longer. From our perspective on Earth, the Large Magellanic Cloud is one of our nearest galactic neighbors, but at 160,000 light-years, it's still an enormous distance. For most of the history of astronomy, individual stars in other galaxies have been impossible to resolve directly. Other galaxies appear as smooth glows of combined starlight. We can study the average properties of those galaxies, but we can't see individual stars within them, except in special cases like supernova explosions, which briefly become bright enough to dominate their host galaxies. This is one of the central frustrations of extragalactic astronomy. The universe is mostly full of galaxies, not individual stars. We can map the cosmos, count galaxies, measure their motions and compositions. But within each galaxy, the individual stars blur together. Even our nearest neighbors, the Magellanic Clouds, Andromeda, the Triangulum Galaxy, appear in most images as collective masses rather than collections of resolvable points. WOHG 64 is special because of 2 things. First, it's intrinsically extraordinarily bright. Bright enough to stand out even at 160,000 light-years. And second, it's surrounded by a thick dust cocoon that has unusual properties, making it a natural target for detailed study. The dust cocoon was the first hint that WOHG 64 was something special. As far back as the 1980s, astronomers noticed that the star was extraordinarily luminous in infrared light, much more so than expected from its visible brightness alone. The infrared excess was a signature of dust surrounding the star, hot enough to glow at infrared wavelengths, but cool enough that the dust itself remained intact. The dust was being heated by the star inside it. The amount of dust suggested significant mass loss. WOHG 64 had been throwing material into space for a long time, but the star itself remained unresolved. Even the best telescopes of the 1990s and 2000s couldn't separate the star's image from the dust cocoon around it. You could see the combined glow. You couldn't see the components individually. That changed in late 2024. A team, using the European Southern Observatory's Very Large Telescope Interferometer, VLTI, for short, captured something that had never been done before, a direct image of an individual star outside our own galaxy. They imaged WOHG 64. The technique used to do this is called interferometry. It works by combining the light from multiple separated telescopes, treating them as if they were a single, much larger telescope. The resolution of a telescope depends on how large its mirror is. Bigger telescopes can see finer details. With interferometry, you can effectively combine separate telescopes into a virtual telescope as large as the distance between them. The VLTI uses 4 8-meter telescopes spread across a hilltop in Chile's Atacama Desert, with separations of up to 200 meters between them. That gives the VLTI the equivalent angular resolution of a 200-meter telescope, even though no actual mirror is that large. With that resolution, the VLTI can resolve features approximately as small as the apparent size of a coin viewed from 1,000 kilometers away. It's still not enough to see Earth-sized planets around other stars, but it is enough to see the actual disk of a red supergiant in another galaxy. The image was remarkable. They could see the star's surrounding dust shell, shaped like an extended egg or cocoon, evidence of uneven material ejection. They could see hints of the star itself, partially obscured by the dust. And by comparing observations from different years, they could see that the star was changing. WOHG 64 appeared to be transitioning, possibly shifting from a red supergiant state into something else. Perhaps a yellow hypergiant phase, perhaps approaching its supernova event. The yellow hypergiant phase is a rare transitional state that some massive stars pass through near the end of their lives. The star contracts slightly and heats up, shifting its color from red toward yellow as the outer envelope changes structure. The phase doesn't last long, perhaps a few thousand years at most, before the star either stabilizes back into a red supergiant or progresses towards supernova. If WOHG 64 really is in this transitional state, we're watching something extraordinarily rare. Possibly we are observing the final stages of a single star's life, an event that takes a few thousand years total, captured in detail across a distance of 160,000 light-years. The implications are still being worked out. Subsequent observations over the coming years and decades will reveal whether WOHG 64 stabilizes or continues toward eventual explosion. WOHG 64's radius is estimated between 1,540 and 1,730 solar radii. Smaller than the Stevenson stars claimed 2,150, but with much smaller uncertainty bars. We can actually see WOHG 64. We have a direct image of it. The size estimate is grounded in observed angular diameter, not just inference from luminosity and temperature. Some astronomers argue that WOHG 64, not the Stevenson star, should be considered the largest confirmed star, the biggest one whose size we can verify directly rather than infer indirectly. This star might be larger, but we don't have a picture of it. WOHG 64 we've actually seen. There's a real philosophical question embedded in this disagreement. What does it mean to know a star's size? Is the largest known star the one with the highest claimed number, even if the number is uncertain? Or is it the one whose number is most reliable, even if smaller? Different astronomers answer this differently. There's no single right answer. For the Stevenson star specifically, the working consensus is approximately the star is among the largest known, but the figure could be revised in either direction by future measurements. In popular discussions, the qualifications often disappear. The Stevenson star gets called the largest star, without caveats. That's not a misrepresentation exactly, but it does flatten the actual state of knowledge. What's certain is that both the Stevenson star and WOHG 64 are among the biggest stars currently known. They might both be the largest, depending on which uncertainties you're willing to accept. They might both be smaller than something else we haven't found yet. There are other contenders worth mentioning briefly, because the field is crowded. NML Cygni is a red hypergiant in the constellation Cygnus. It was once claimed at 3,700 solar radii, which would have made it almost twice the size of the Stevenson star. Subsequent revisions have brought it down to a range of 1,183 to 2,770 solar radii. The range of possible values is so wide that NML Cygni might be the champion, or it might be smaller than several other contenders. Without better data, we can't say. NML Cygni was discovered in 1965 during a survey for stars that were extremely luminous in infrared, but very faint in visible light. The pattern indicated a cool, dusty object, which turned out to be a red hypergiant heavily obscured by its own ejected material. The star is about 5,300 light-years from Earth. It has been studied for decades, but its precise properties remain elusive because of the obscuring dust around it. The 3,700 solar radii claim came from early measurements that assumed a specific distance. Later, more refined distance estimates brought the radius down. The current best range, 1,183 to 2,770, reflects ongoing disagreement about exactly where the star ends and the dust begins, and exactly how far away the system is. NML Cygni illustrates the problem in microcosm. The same star can be ranked as the largest or merely large, depending on which assumptions you adopt. Westerland 126, located in the galactic open cluster Westerland 1, is another candidate. Current estimates put its radius between 1,500 and 2,500 solar radii. The same wide margins problem applies. The Westerland 1 cluster itself is one of the most massive young star clusters in the Milky Way, possibly home to a future globular cluster, the kind of densely packed stellar swarm that orbits the outer regions of galaxies. The cluster contains a remarkable variety of evolved stars: red supergiants, yellow hypergiants, Wolf-Rayet stars. Westerland 126 is the most extreme of the red supergiants in the cluster, but it's surrounded by other stars only slightly smaller. The cluster's age, around 4 to 5 million years, places it at exactly the right stage for massive stars to be ending their lives. RSGC1, FO1, is in the red supergiant Cluster 1, a sister cluster to Stevenson 2. It has a similar mass to the Stevenson star, but a smaller current radius estimate, around 1,500 times the radius of our own star. The fact that two of these enormous clusters exist in roughly the same region of the galaxy suggests that the inner Milky Way passed through a period of very active massive star formation a few tens of millions of years ago, leaving behind these dense pockets of dying giants. This star was discovered in 2006 and contains over a dozen confirmed red supergiants packed into a region roughly 7 light-years across. The density of red supergiants in this cluster is unlike anything else in our region of the galaxy. Stars that should be statistically rare are crowded together here, the product of a single massive star formation event that all reached their red supergiant phases at approximately the same time. These clusters are time capsules of a particular moment in galactic history. They tell us that massive star formation comes in bursts. Whatever triggered the formation of RSGC1, RSGC2, Stevenson 2, and the other red supergiant clusters in this region, possibly a collision with another structure, possibly a passage through a galactic spiral arm happened around 10 to 20 million years ago. The stars that formed during that event are now simultaneously all reaching the ends of their lives. In another few million years, most of these clusters will have exploded their stars away, leaving behind sparse remnants of neutron stars and black holes drifting through space. VY Canis Majoris, the former champion, has been revised down to about 1420 solar radii. Still extraordinary, still one of the largest known stars, no longer the largest. VY Canis Majoris has a special place in this story because it was once the headline example used in popular astronomy. For roughly 20 years, the original inflated estimates of VY Canis Majoris's size dominated public discussion of largest stars. Images and animations compared it favorably to UY Scuti and other contenders. When the revisions came, popular culture lagged behind. Even today, you can find articles and videos claiming VY Canis Majoris is the largest known star based on estimates that working astronomers updated more than a decade ago. This is one of the challenges of public communication about astronomy. The cutting edge of measurement moves faster than popular understanding. By the time educational materials catch up with current measurements, the measurements have often been revised again. Betelgeuse, the most famous red supergiant of all, is only 887 solar radii. If you placed Betelgeuse at the center of our solar system, its surface would reach approximately to the orbit of Jupiter. That's enormous by any reasonable standard, but it's less than half the size of the Stevenson star. Betelgeuse is special for a different reason. It's close only about 550 light-years away, and it's currently showing signs of instability. In late 2019 and early 2020, Betelgeuse underwent a dramatic dimming event that briefly made it the dimmest it had been in decades. Astronomers initially wondered if it was approaching supernova. The answer turned out to be no. Betelgeuse had ejected a cloud of dust that temporarily blocked some of its light. But the event was a reminder that these stars are unstable and that we're watching them in real time. The 2019-2020 dimming was striking enough to attract worldwide attention. Betelgeuse dropped from being one of the 10 brightest stars in our night sky to barely making it into the top 50. People who had grown up seeing the same star pattern in Orion suddenly noticed that one of its key landmarks had faded. For several months, social media and news outlets speculated about whether the star was about to explode. The actual cause turned out to be more mundane but still scientifically interesting. Detailed observations revealed that the star had ejected a large blob of gas and dust from its surface. That ejected material, drifting outward, cooled enough to condense into solid dust grains. The dust temporarily blocked our view of part of the star's surface, dimming its apparent brightness even though the star itself hadn't actually changed much. By mid-2020, the dust had dissipated enough that Betelgeuse returned to roughly its normal brightness. But the event taught astronomers something. These massive stars are not just slowly shedding material, they're sometimes throwing off discrete clumps, irregular ejections that travel outward and form temporary structures around the star. The material doesn't leave the star smoothly. It departs in clumps and bursts, unpredictably. The Stevenson star almost certainly does the same thing. We just can't see the events in real time because the star is too far away and too obscured by intervening dust. The slow average of mass loss that we measure includes thousands of these clumpy ejections blurred together by distance. When Betelgeuse eventually goes supernova, and it will, sometime in the next 100,000 years or so, it will become the brightest object in our night sky after the moon. For weeks, possibly months, it will outshine Venus. Possibly even outshine the moon during certain phases. It will cast shadows. It will be visible during daylight. And then it will fade. If you want to see what the Stevenson star's eventual death will look like, watch Betelgeuse. Whichever one goes first, the other will look much the same from a distance. It's worth noting, just briefly, that Betelgeuse going supernova would be perfectly safe for Earth. At 550 light-years, it's well outside the danger range for a supernova to cause damage to our planet. The energy released would be enormous, but spread thin by the time it reached us. We would see an extraordinary light show lasting weeks. We would feel no other effects. The expanding shockwave from the explosion would take hundreds of thousands of years to reach us, by which time it would be a faint, expanding nebula rather than a violent shockwave. There are also, briefly, theoretical stars that may have existed in the early universe, population 3 stars, and so-called quasi-stars. Population 3 stars were the first generation of stars formed from the pristine hydrogen and helium of the early universe before any heavier elements had been created. Computer simulations suggest some population 3 stars may have been hundreds of times more massive than anything alive today, and correspondingly enormous in size. Quasi-stars were a hypothesized type of object, where a supermassive star formed around an early black hole, with the black hole at its core feeding on infalling material while the outer envelope behaved like a star. The population 3 era is fascinating to think about. In the first few 100 million years after the Big Bang, the universe contained only hydrogen and helium. The conditions for star formation were different. Without heavier elements to cool gas clouds, those clouds had to be more massive to collapse and form stars. The result, according to simulations, was that early stars were much more massive on average than stars today. Some may have been 1,000 solar masses or more, extraordinarily massive, extraordinarily short-lived, and almost certainly enormous in their final red supergiant phases. We have never observed a population 3 star directly. They're too far away in time and space. The light from those stars has been traveling for over 13 billion years to reach us, and the universe's expansion has stretched their wavelengths so dramatically that what was once visible light is now extreme infrared or radio. The James Webb Space Telescope is one of the first instruments capable of looking for them. But even with JWST, definitive population 3 star observations are still rare and uncertain. Quasi-stars, if they existed, would have been astonishingly large, possibly tens of thousands of solar radii. But we have no observations of them. They lived briefly, died quickly, and left no remnants we can study. They're hypothesized to explain certain features of the early universe, particularly the existence of supermassive black holes already in place during the first billion years after the Big Bang. The supermassive black holes we see today couldn't have formed from ordinary stellar deaths in that time frame. Something must have been growing very fast. Quasi-stars are one of the proposed explanations. These hypothetical objects are part of the story of largest stars, even though we can't observe them. They represent a possible upper bound to what nature could produce under conditions that no longer exist. The universe of 13 billion years ago was different from today's universe. Star formation worked differently. The largest stars in that ancient cosmos may have been many times larger than anything we can find in the modern universe. But we have to set them aside. They're not part of the catalogue of observed objects. They're theoretical. They might have been real, or they might not have been. Either way, we can't directly compare them to the Stevenson star. The honest summary is that we have a list of candidates for the largest star in the observable universe. None of the measurements are perfectly clean. The error bars overlap. The Stevenson star sits at the top of the list by raw radius, but its measurement is also the most contested. WOHG 64 has the most confident measurement, but a slightly smaller nominal size. NML Cygni and Westerland 126 have measurement ranges so broad they include both possibilities. They might be larger than this star, or they might be smaller than Betelgeuse. This is the actual state of the field. We have candidates. We don't have a definitive answer. The label largest known star is provisional and probably always will be. Every red supergiant we've discussed tonight is going to die. Some of them probably already have, and the light of their deaths is still traveling toward us, decades or centuries away from arrival. A red supergiant dies when it runs out of fuel. We've talked about how stars work the balance between gravity and radiation pressure, with fusion in the core providing the energy. For most of a star's life, that fusion is hydrogen turning into helium. Then, in the red supergiant phase, helium fuses into carbon. Then, if the star is massive enough, carbon fuses into oxygen and neon. Then, heavier elements still, all the way up. But there's a problem. Each successive stage of fusion produces less energy than the last, and the products of each stage are getting closer to iron. Iron is the wall. Iron is the heaviest element a star can produce through fusion past iron. Fusion absorbs energy instead of releasing it. So when a massive star starts fusing iron, the fusion process actually consumes more energy than it generates. The reason iron is special comes from the basic physics of how atomic nuclei work. The strong nuclear force holds protons and neutrons together in atomic nuclei, but it has a peak efficiency. Iron sits at exactly that peak. Atoms lighter than iron can release energy by fusing into heavier elements. That's what stars do for most of their lives. Atoms heavier than iron can release energy by splitting into lighter elements. That's what nuclear reactors and fission bombs do. But iron itself can do neither. It's energetically stable. Trying to fuse iron costs more energy than you get back. Trying to split it does the same. Iron is the dead end of stellar nuclear fuel. The star is essentially out of fuel. Gravity is no longer being held back by radiation pressure. The core collapses. This is not a slow process. It's not over years or decades. The collapse of a massive stellar core happens in less than a second. The core falls inward, compressing matter to densities greater than the densities inside atomic nuclei. The compression releases an enormous amount of energy in the form of neutrinos and gravitational waves. Most of that energy escapes directly into space, invisible, but a fraction of it slams into the still-infalling outer layers of the star and reverses their motion, blowing them outward in a colossal shockwave. That shockwave is the supernova. The amount of energy released in a single supernova is difficult to convey. In the span of a few seconds, the star releases more energy than our own sun will produce in its entire 10 billion-year lifetime. The visible light from the explosion peaks over a few weeks. The shockwave races outward at thousands of kilometers per second, eventually plowing into the surrounding interstellar medium and forming a glowing nebula that can be seen for thousands of years afterward. Most of the energy from a supernova, though, isn't visible at all. About 99% of it leaves as neutrinos, ghostly particles that barely interact with normal matter. These neutrinos pass through entire planets without slowing down. They pass through us, billions of them every second, even from supernovae that occurred long ago and far away. If you knew when a nearby supernova was coming, You could detect the neutrinos arriving on Earth several hours before the visible light. The neutrinos travel slightly faster than the light, because the light gets delayed by interactions with the star's outer envelope as it escapes. For approximately the next 2 to 3 weeks, a single dying star produces more visible light than entire galaxies. The explosion can be seen from across the universe. If a supernova goes off in our galaxy at a comparable distance to the Stevenson star, it would be the most visually dramatic event in human history. It would be brighter than the full moon. It would be visible during the day. It would change color over weeks, fading from blue to white to yellow to red as the expanding shockwave cooled. We've seen supernovae before. There are historical records of them, the Chinese guest star of 1054, which we mentioned earlier. The supernova of 1572, observed by Tycho Brahe. The supernova of 1604, observed by Johannes Kepler, SN 1000. 987A in the Large Magellanic Cloud, which was the first naked-eye supernova of the modern era in February 1987. The 1054 event is worth lingering on. Chinese imperial astronomers, who kept detailed records of the night sky for ceremonial and astrological purposes, noticed in July of that year a new star in the constellation we now call Taurus. They called it a guest star, using a term they reserved for unusual celestial events. The star was so bright that it was visible during the day for 23 days and remained visible at night for 21 months before fading from view. Their records survived. We can read them today, nearly 1,000 years later, and we can correlate the position they described with what we now know is the Crab Nebula, the expanding remnant of that supernova, still visible in our telescopes, still spreading outward into space at thousands of kilometers per second after nearly a millennium of expansion. Arab astronomers also recorded the 1054 event. Native American petroglyphs found in the American Southwest appear to depict the supernova too. Across multiple continents and civilizations, humans noticed the same explosion and recorded it in their own ways. The light from that single dying star reached Earth all at once after a journey of approximately 6,500 years through empty space. None of those historical supernovae were from stars as large as the Stevenson star. The Crab Nebula's parent star, the 1054 event, was probably only about 10 solar masses initially. This star is at least twice that, possibly 3 or 4 times that. When it goes, the explosion will be substantially more energetic than any supernova we've recorded in human history. What gets left behind depends on the star's mass. For lower mass red supergiants, say 10 to 20 solar masses, originally the core collapses into a neutron star. A neutron star is approximately the mass of our own sun compressed into a sphere about 20 kilometers across. The matter inside is so dense that neutrons are packed essentially shoulder to shoulder. A teaspoon of neutron star material would weigh approximately 100 million tons on Earth. Or, looked at another way, the entire population of Earth, all 8 billion people, compressed into a sugar cube. The transition from a red supergiant, the size of Saturn's orbit, to a neutron star, the size of a small city, is one of the most extreme transformations in nature. In a matter of seconds, an object that took up trillions of cubic kilometers gets compressed into something that would fit inside a metropolitan area. The mass is the same. The density goes up by something like 15 orders of magnitude. Neutron stars have surfaces that are not really surfaces in the usual sense. The matter inside is degenerate, meaning quantum mechanical effects determine its behavior, not classical chemistry. The exterior crust is the only place where anything like normal matter exists, and even that is unusual. Iron nuclei arranged in a rigid crystalline lattice with extreme magnetic fields permeating everything. Neutron stars are also remarkable for what they do next. Many of them spin extremely fast. The fastest known neutron stars rotate hundreds of times per second. As they spin, they emit beams of radiation from their magnetic poles, which sweep across space like lighthouse beams. From Earth, if the beam happens to point toward us during each rotation, we see pulses of radio waves at extraordinarily regular intervals. We call these objects pulsars. They were discovered in 1967, before astronomers knew what they were, and their precise regularity was so striking that researchers briefly wondered if they might be artificial signals from another civilization. They're not. They're dead stars spinning. The discovery of the first pulsar by Jocelyn Bell Burnell, then a graduate student in Cambridge, is one of the great stories of 20th century astronomy. The signal was so unexpected, so precisely regular, that her initial label for it in her notebook was LGM1, standing for Little Green Men. It took some time to rule out artificial origins. Once natural causes were established, the signal was understood as the rotating beam of a neutron star, and the field of pulsar astronomy was born. For more massive red supergiants above 25 or 30 solar masses, initially the core collapses past the neutron star stage. There's no force in the universe strong enough to stop the collapse. The matter falls in on itself indefinitely, becoming a black hole. This is where the connection to last week becomes relevant. In the previous video, we walked through the scale of black holes from city-sized stellar black holes up to Ton 618, the supermassive monster at the center of a distant galaxy. The smallest black holes in that range, the stellar mass black holes, are exactly what red supergiants like the Stevenson star produce when they die. The chain is straightforward. A massive cloud of gas collapses and forms a star. The star burns through its fuel over millions of years, growing increasingly bloated in its final stages. Eventually, it can fuse no more, and the core collapses. If the original star was massive enough, the collapse produces a black hole. That black hole sits in space, a small, dense, dark object for the rest of the universe's existence. Black holes don't disappear. They don't evaporate quickly. The tiny amount of Hawking radiation they emit means they technically lose mass over astronomical timescales. But for a stellar mass black hole, that timescale is something like 10 to the 67th power years. The universe has only existed for 14 billion years. The black holes we've made are essentially permanent on any timescale that matters. So the Stevenson star, when it dies, possibly soon, possibly in 100,000 years, will likely leave behind a black hole. Not a particularly large one. Maybe 5 to 15 solar masses. The kind of object we now know to be incredibly common in the Milky Way. There are tens of millions of these objects scattered throughout our galaxy, the remnants of dead massive stars going back through galactic history. We don't see them because they emit no light of their own. They're black holes. They're dark, in the most literal sense possible. We only detect them when they're paired with companion stars and pulling material off those companions, which heats up and emits X-rays. Or when two of them merge, releasing gravitational waves we can detect with LIGO. Or when they pass between us and a more distant star and bend its light gravitationally. In microlensing events, the Milky Way is full of these objects. Most are invisible. Some will pair up with other black holes over billions of years, slowly spiraling into each other and eventually merging. The mergers add up. Over enough time, with enough mergers, you can build supermassive black holes from the bottom up. though that's only one of several possible formation pathways for the truly enormous ones. When the Stevenson star eventually dies, its corpse will be one more entry in the catalogue. One more stellar mass black hole drifting through the galaxy, invisible to most observation. Its position will be poorly known. Its presence will eventually be forgotten. The star that once stretched across the inner solar system will leave behind an object smaller than the city of Tokyo, but containing more mass than 1,000,000 Earths. This is the strange thing about these enormous objects. They produce, in their death, some of the smallest dense objects in the universe. The biggest matter the universe can make collapses into the smallest matter the universe can make. Bigness in stars is a temporary state. The end state is always compact, always dense, always extreme. Everything that exists is on its way to becoming something else. We've talked tonight about a particular star in a particular cluster with particular measurements that we can't entirely trust. We've talked about how stars become enormous and how we estimate their sizes and what happens when they die. We've placed the Stevenson star in context with its competitors WOHG 64, NML Cygni, Betelgeuse, and the others. Let me end by stepping back. Stars like the Stevenson star are rare, genuinely rare. There might only be a few dozen stars of this scale in the entire Milky Way at any given moment. The galaxy contains somewhere between 100 and 400 billion stars, and only a vanishingly small fraction of them are passing through the red supergiant stage at any given time, because that phase lasts only a few 100,000 years out of a typical massive star's multi-million-year lifetime. We're catching them at a brief window near the end of their lives. To put this rarity in perspective, imagine a city of 100 million people. The proportion of massive stars in the galaxy currently in the extreme red supergiant phase is roughly equivalent to picking out one specific person from that city. They exist. They are real. They are out there. But they are statistically unusual, and finding them requires deliberate, systematic searching. This means that the population of largest stars is constantly turning over. The Stevenson star we see today did not exist 100 million years ago. It will not exist 1,000,000 years from now. The catalogue of largest known stars is a snapshot of a single moment in galactic history. In a different moment, the candidates would be entirely different stars. Different objects, in different places, all going through their own brief red supergiant phases. The Milky Way has been making stars for 13 billion years. Many trillions of stars have lived and died inside our galaxy in that time. Most of them were smaller than our own star. Most of them are dim red dwarfs that will still be alive long after our sun has burned out. But a small fraction, perhaps one in a few thousand, were massive enough to eventually become red supergiants. Each of those, briefly, was one of the biggest objects in the galaxy. Each of those eventually exploded. There have been thousands of red supergiants that came before the Stevenson star in the history of our galaxy. There will be thousands more after it. The matter that is currently bound up in this star was once bound up in earlier stars that died long ago. The matter that the star sheds into space over its remaining lifetime will eventually be bound up in stars that don't exist yet. The universe is, in this sense, a recycling system at galactic scale. Atoms forged in early stars get scattered by supernovae, drift through the interstellar medium, get pulled into new star-forming regions, condense into new stars, and eventually get scattered again. Most matter has been through this cycle many times. The carbon atoms in your body have probably been inside multiple stars before they ended up in you. Each of those stars lived, swelled, died. Each released the carbon back into space. Each time, the carbon got incorporated into the next round of stars and planets. We are, all of us, part of an ongoing process that started before us and will continue long after us. The largest stars we see today are temporary configurations of this process. They are, in their brief moment of being, the most extreme version of what stars can do. And then they end, and the matter moves on to become something else. The universe has been doing this for as long as it has had stars. And the universe has not run out of material to make more. Somewhere out there, right now, possibly in a region of the galaxy obscured by dust, possibly in a galaxy we haven't surveyed in detail, there's an even larger star alive. A red supergiant we haven't discovered. A star whose measurements, when we eventually take them, will displace the Stevenson star from the top of the list. We can be reasonably confident this is true because of statistics. We have surveyed only a small fraction of the Milky Way in detail. Most of the galactic disk is hidden from us by intervening dust and stars. Most of the inner regions of the galaxy, where massive star formation is most active, are obscured by the dense crowd of stars and gas between us and them. There are entire regions of our own galaxy that we have not been able to inventory carefully. Some of those regions almost certainly contain red supergiants we haven't found yet. Some of those might be larger than the Stevenson star. The catalogue is never finished. There is always another candidate, somewhere we haven't looked. Better telescopes, better measurements, better techniques will keep updating the list. Some of the entries currently on it will be revised downward, like UY Scuti was. Some new entries will be added. The crown of largest known star will pass from one object to another as the data improves. In 100 years, the largest known star will probably not be the Stevenson star. We will have found something bigger, or measured this star more accurately and found that it was smaller than we thought. Or both. This is not a failure of our current knowledge. It's how the search works. We observe, we publish, we refine. The truth slowly clarifies, never completely, but always a little more than before. What stays true through all the revisions is the basic fact that the universe makes things on this scale. Red supergiants exist. They are real. They are out there right now, glowing dimly in obscure constellations, swelling toward their final supernovae. Some of them are absurdly large. The largest are larger than anything our solar system could contain. They live for blinks of time, and then they die spectacularly. And then their remnants drift in silence for the rest of cosmic history. You are made of atoms that were once inside stars like these. Not these exact stars, but earlier generations of similar objects. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it was fused inside the cores of red supergiants long ago, then scattered into space when those stars died, then eventually incorporated into the cloud of gas that became our solar system. You and the largest star we've ever found are made of the same stuff. The difference is just how that stuff is currently arranged. Lie back. Close your eyes if you haven't already. The universe is still out there, doing what it has always done. Stars are being born. Stars are dying. Somewhere in the Scutum constellation, a red supergiant called the Stevenson star is shedding mass into the dark, slowly building up the dust cocoon that will surround its eventual supernova. In another galaxy, WOHG 64 is transforming, possibly approaching its own end. Other contenders we haven't found yet are doing the same thing in places we haven't looked. The largest star we've ever found is not the largest star that exists. It's just the largest one we currently know about. There's something quietly profound about that distinction. It tells us we are small, our knowledge is incomplete, and the universe will always have surprises for us. But it also tells us we are part of the search. We are the ones doing the looking. We are the species that, after billions of years of cosmic evolution, finally turned its attention outward and started cataloging the largest things in existence. That counts for something. Think about the chain of events that had to happen for this to be possible. The Big Bang produced hydrogen and helium. Those gases coalesced into the first stars, which lived and died, scattering heavier elements into the cosmos. Those elements went into second-generation stars, which also lived and died, producing even heavier elements. After multiple generations of stellar life and death, the matter that would become our solar system finally formed around 4.5 billion years ago. Earth condensed out of that material. Life appeared on Earth's surface. Life evolved into increasingly complex forms. Eventually, one branch of life developed the cognitive capacity to look up at the sky and wonder what was up there. It took the universe approximately 10 billion years of star formation and stellar death to produce the conditions for life. It took life on Earth approximately 3.5 billion more years to evolve into something capable of asking questions about stars. And in just the last few hundred years, a vanishingly small fraction of cosmic time, we have moved from the stars are tiny lights stuck on a celestial sphere to a detailed catalogue of red supergiants larger than our entire inner solar system. That's an astonishing pace of learning. We don't always feel like we're making progress, but on the timescale of cosmic history, our progress has been remarkable. The universe keeps making things bigger than we expect, and we keep finding them, slowly, one telescope at a time, across hundreds of years of patient observation. If you found this video calming or interesting, or both, there should be another video appearing on screen now. It's another long-form journey through one of the most extreme objects we've catalogued in the universe. The same gentle pacing, the same slow narration, the same approach. Lie back, settle in, and let yourself drift into another story. Good night.